Let's start. So this is week 5 of Physico Chemical processes for wastewater treatment. This is online live session for the assignments. I am Vaibhav Kabadwal, PhD scholar from IIT Madras. I am the TA for this course. So let's start this session. So in this session, we will study about some part of coagulation and flocculation and some part of settling and sedimentation. So we will solve some MCQs, fill in the blanks, match the following, and few numericals. So in coagulation and flocculation, let's solve some MCQs. Read the question. The best coagulant could be chosen usually by which laboratory test? So the and choices are COD. COD is for organic matter. Jar test. Jar test is for optimum coagulation dose. Coagulant dose. Optimum coagulant dose. BOD is for biodegradable organic matter. Organic matter. Fecal count is for fecal coliform. Fecal coliform are the group of organisms which act as indicator of uh, microbes which are present in the feces. So they will tell uh, like the water is contaminated with microbes or not, harmful microbes. Water is contaminated with disease causing microbes. So the answer is the best coagulant could be chosen usually by which of the following laboratory test. So this can be chosen with the help of jar test only. B is the correct answer. Flocculation settling is applicable for dilute suspension of particles that coalesce or flocculate. Flocculation settling is applicable for dilute suspensions of particles that coalesce or flocculate. Correct. So what we can conclude here, in type 1 and 2 we have dilute suspension. But in type 3 and 4 suspension is concentrated. Concentrated solution suspension. Suspension will be a better word. So in type 2 what happens, the particles, like in type 1 particles will settle discretely. Suppose this is a tank, but even it is in tank, but water is coming from this place and going out this. So in discrete particle settling, the particles will not interfere with each other. But in flocculant, like we studied, uh, coagulation aided flocculation. So with the time, so with the depth, they will form a bigger flock. With depth, it will form the bigger flock, and its velocity will change with time. So in type 2, let's make it clear. Yes, in type 1 settling, discrete particles will not interfere with each other. They will settle independently. In type 2 settle, in type 2, they will form flock. The suspension here is dilute in both. Means the concentration of particles is less in both the suspension. So form flocks and then settle. In type 3, they will interfere with each other. Interfere with each other, and uh, they will settle like a layer. Settle like layer. Their velocity field will overlap. Their velocity field overlaps. In type 4, particles are so close. Particles are so close. These are the main characteristics of different types of settling. So in type 4, the particles are so close that water will water comes uh, comes out of interstices. So suppose if particles are so close, like when they settle, so the water will come out while settling. So these are the main key points for each type of settling. So in MCQs we will see further details. One more MCQ is here. The best coagulant could be chosen usually by which of this is done. Now question. A water treatment plant treating 50 into 10 to the power 6 liter per day of water. Okay, so we are treating 50 mld of water per day, which requires 20 milligram per liter of alum. If the water has 6 milligram per liter of alkalinity, determine the first. There are two things to find out. Quantity of alum required per day and year. Quantity of, so this will be not alum, this will be alkalinity. We will change it. Alkalinity uh, in terms of, let's say, CO required per day and year. So we will solve this question. So what all things are given? So the question says flow rate is 50 to 10 to the power 6 liter per day, and alum requirement is 20 milligram per liter, and alkalinity present. Alkalinity present is 6 milligram per liter. So we will see what is the reaction of alum first. So the alum, this is alum, this is the formula of alum. Alum reacts with alkalinity and it forms this AlOH3. This is the precipitate, and it forms carbon dioxide, CaSO4. This is actually permanent hardness, and water molecules. So what we can say, alum reacts with alkalinity and produces this permanent hardness, CO2 gas, and aluminum hydroxide precipitate. So this will be, so our main concern is to know about these two things, alkalinity and this this is called sludge. So this precipitate, it will get precipitated and it will form sludge, AlOH3. So first we'll consider uh, alum. So let's find out the molecular weight of these things. Let's take alum. So alum is Al2SO4 318S2. So 27 into 2 plus 32 plus 16 into 4 plus 18 into 18. You solve it, you will get 666 grams. For alkalinity, you can calculate either in terms of CaHCO3 twice, or CaCO3, or uh, Ca also, in whatever form you want to calculate. So let's calculate here for second we will go for AlOH3. Then we'll alkalinity is comparatively bigger than this AlOH3, so we'll discuss it later. So AlOH3, 27 plus 16 plus 1 into 3. So how much will it come? 27 plus, okay, it's coming with like 78. 78 grams. Let me check it. Correct. These two are correct. So from here, what we can conclude, that 666 grams. Let's not write like this. We'll write like 1 mole of alum will produce 2 moles of sludge. 1 mole of alum forms 2 moles of AlOH3. So 1 mole of alum means 666 grams, and 2 moles of AlOH3 will be 2 into 78. So 1 grams of alum will produce 2 into 78 divided by 666 grams. So how much? It will be 0.234 grams of AlOH3. Okay, so this is for sludge. Now we will calculate for alkalinity. So for alkalinity, what is the 3 moles required? So CaHCO3 twice. CaHCO3 twice. So in question they can ask in the form of CaHCO3, they will ask, they may ask like how much quantity of CaHCO3 twice is required, or they may ask how much CO is required, or they may ask how much CaCO3 in terms of CaCO3 alkalinity is required. So we'll formulate like how it can be done. So one concept which we use here is that is simple. That is the concept of equivalent that we taught earlier also. Concept of equivalent. It says that one equivalent of anything reacts with one equivalent of any other thing. So basically, we have read this statement N1 V1 is equals to N2 V2. So if you solve it, you will understand it is nothing but equivalent. N1 V1 is nothing but equivalent. So in our case, like CaSCO3 twice, so it has a combining capacity so of 2, and CaO it also has the combining capacity 2, and CaCO3 so it also has the combining capacity 2. So here in all three cases we can write their 1 mole is equal to 2 equivalents, correct? 1 mole is equal to 2 equivalents because their combining capacity or valency is 2 in all three cases, correct? So now I will write their molecular weight. Molecular weight is 40 plus 1 plus 12 plus 16 into 3 into 2. Here it will be 40 plus 16. It will be 56. It will be 40 plus 12 plus 16 into 3. So this we know 100, and this we need to calculate. It will come, I think, 161. Yeah, 162. Solving you will get it as 162, 56 grams, 100 grams. So this is the molecular weight and molecular weight and combining capacity. Combining capacity is 2 for all three cases, and now their equivalent weight will be molecular weight divided by combining capacity. It will be 81 grams. It will be how much? 28, I think. 28 grams. 50 grams. So let's see how much alkalinity is required in our. So we can write from like this. Let's not write like this. Let's write like this. 1 mole of alum requires, I think, 3 moles. That is that equation. 3 moles of alkaline. 1 mole of alum 1 mole of alum requires 3 moles of CaHCO3 twice. This is alkalinity. Or we can say it like 1 mole of alum requires 3 moles of CaHCO3 twice, or 3 moles of CaO, or 3 moles of CaCO3. Correct? And you can write like 3 into 1 mole is 666 grams of alum. 3 into how much? 161. 3 into 56. 3 into 100. So if we solve it, 3, 3, 3 into 161, 483, 480 grams. 3 into 56, 168 grams. And 300 grams. So this is in terms of CaCO3, in terms of CaO, in terms of CaCO3. So if I need to find it for 1 grams, how much will it be? 483. Let me check whether it is correct or not. Oh, it is 162 actually. So 3 into 162, then 3 into 162, 486. So for 1 gram, it will come as 0.729 grams. And that will come as 0.252 grams. And it will come as 0.45 grams of CaCO2. So now we can solve our question. So this is the question. So we are given discharge, flow rate, alum dose, and alkalinity present. So what happens? Alum from the previous alum equation we understood that alum requires alkalinity. So whether that alkalinity is sufficient or not, we will calculate how much alkalinity is required based on the stoichiometric equation. And if alkalinity is plentifully available, then we need not to require the CO requirement. But if this alkalinity is less than the required alkalinity, then we will calculate how much CO is required. Now let's proceed. So first we will find out the LM requirement. LM requirement. How much LM is 20 milligram per liter? So we are given 20 milligram per liter. We'll directly convert it into tons. So it will be minus 6 will convert it into kgs, and minus 3 will convert it into tons per liter. And then we have flow rate of around 50 into 10 to the power 6 liter per day. Correct? Let me cross check. Yeah. So we can cancel these two, and the requirement will be 20 into 10 to the power minus 3 into 50. The requirement is 1 ton per day is the LM requirement. See how much LM is required per day for 50 mld, 50 mld water or wastewater. So this is per day for an year. It will be 365 into requirement per day, LM requirement per day. That will be 365 into 1, that is 365 tons per day. This is the LM requirement. Okay. Now we will proceed for alkalinity requirement. So we directly calculate CO required. We have formulated here. So 1 gram of alum, 1 gram of alum requires 0.252 gram of 0.252 gram of alkalinity in terms of CO. But in the question, we are given alkalinity in terms of CaCO3 also. So here we will start with CaCO3 only. So alkalinity present. So first we will calculate alkalinity present. Alkalinity present. So present how much? Is 6 milligram per liter. We'll do the same thing. Convert it into minus 3 kg per liter. Then we'll first phosphorus to be minus 6. To be minus 6 kg per liter. And then we'll multiply it with minus 3. Will be ton per liter. Then we multiply it with 50 into 10 to the power 6 liter per day. This is a per day demand of, this is the alkalinity present. 6 6 power 6 into 50 into 10 to the power minus 3. This is the requirement of, and this one is alkalinity is present. 0.3 tons per day. And alkalinity required, let's calculate. I will write here in terms of CaCO3 because we calculated it, because this is given in terms of CaCO3. Alkalinity required. So what we are doing in this question, the already the given alkalinity is in terms of CaCO3. Here, 6 milligram per liter. So we will calculate what is present in terms of CaCO3 and what is required in terms of CaCO3. And if the requirement is more than the present alkalinity, we will subtract. So that much amount will be provided by us. So that we will also calculate in terms of CaCO3. And then we will convert that alkalinity to be supplied. Then we will convert in terms of CaO. So this is the approach which we will use here. Alkalinity present, alkalinity required. That is also in terms of CaCO3. How much alkalinity required? We understood from this equation for 1 gram of alum, for 1 gram of alum, 0.45 grams of 0.45 grams of alkalinity required in terms of CaCO3. So I'm writing it here also. For 1 gram of alum, 0.45 grams of alkalinity required in terms of CaCO3. Okay, so how much alum? So based on the alum, we'll try to find out how much alkalinity required. So what we can directly do here. So we are calculating it for 1 day. So alum required per day is 1 ton. Okay, 1 ton per day. So what we can directly say here, for 1 ton, 0.45 tons of alkalinity required in terms of CaCO3. This is correct. So what we can say, 0.45 tons of alkalinity required per day. So now what we can conclude, required per day is 0.45 per day. Alkalinity required per day is this much. So how much alkalinity was present? It was 0.3 only. So now supplied, alkalinity to be supplied. So now what are we doing? So this is A is how much present, B is how much alkalinity required. Now C will be alkalinity to be supplied. supplied will be required minus required alkalinity minus alkalinity present. How much required alkalinity? 0.45 minus point, it was zero point 0.3 I think, zero point 0.3, 0.3 tons per day. Let's calculate it. Minus, yeah, minus 0.45 tons per day. So this is in terms of CaCO3. So let's calculate it in terms of write here it in terms of CaCO3. Alkalinity to be supplied per year. For 1 year. So the alkalinity required will be 365 into 0.15. So it will come out as 54.75 tons per year. And this is in terms of CaCO3. But now we need to calculate in terms of CO. This is the main part. So how can we calculate? We can again go back to the basics. We will see we can compare these two also like this. So for 0.252 grams, 0.45 grams of CaCO3 required. 0.252 is equivalent to 0.45 grams of CaCO3. 0.252 grams of CaO is equivalent to 0.45 grams of CaCO3. Okay, this we are talking in terms of alkalinity. So what we can write, oh, we need to write it in reverse form actually. So 0.45 grams of CaCO3 equivalent to 0.252 grams of CO. So for 1 grams of CaCO3 will be equivalent to 0.252 divided by 0.45 grams of CO. So how much alkalinity required? Uh, let's calculate it. So 1.15 tons per day required. Uh, 0.15 tons required per day in terms of CaCO3. So we'll write 0.15 tons per day of CaCO3 will be 0.15 into 0.252 divided by 0.45. It will be in same units, tons per day of CO. How much it will be? 0.15 into 0.252 divided by 0.45. 0.084. 0.084 tons per day of CO required. Okay, and if we need to calculate it for 1 year, it will be 0.084 into 365. How much? 30.66 tons per year. So this much is the alkalinity required per year, 30.66. So this is the question. Now one more question. What should be the desired characteristics of a coagulant? So if you want to use a coagulant, how will you choose? So the question simply asking, how will you choose a coagulant? Choose a coagulant. You can think like, what is the cost? Because see how much LM was required in the previous question. It was around 1 ton, 1 ton per day and 365 tons per year. Cost, it's you can see this desired characteristics. So how much effective? So effective this we can understand in terms of what is the pH of our wastewater which we are going to treat and whether the coagulant is effective in that pH range or not. So we'll check the effectiveness of the coagulant, we'll check the cost, we'll check the reliability of supply, whether are we getting a continuous supply of coagulant or not, how much sludge is being generated, whether we have facility to dispose the sludge or not. Because most of the time the sludge will be sludge. If sludge is generated, we have to dispose it in the landfills because this is inorganic sludge. This is inorganic sludge most of the time. If inorganic, so it cannot be digested. Okay. Compatibility with other treatment processes. So we need to check whether it is affecting the other treatment processes or not. Whether it requires secondary pollution. So otherwise you have to treat it further. Okay. Capital and operational cost for storage, feeding and handling. Because we need to store the stock if someone is supplying us, so we need to have a stock. So whether like different coagulants have different storage requirements. So we need to see that also and handling requirements also. So we need to see all these characteristics while choosing a coagulant. So now we will move on to settling and sedimentation. So let's understand it with few MCQs. In sedimentation basin, which force is responsible for settling of flocks? So we understood the particles which were not able to settle with the help of gravity. We applied coagulants and polyelectrolyte to settle to make them into a bigger flock, and then they will settle with the help of gravity. So after coagulation, coagulation, flocculation, the water will go into sedimentation chamber or sedimentation basin. There it will settle. There it will settle. It will settle. And the effluent will be taken out. The effluent is taken out. So the entire settlement of flocks is due to gravitational force. In sedimentation basin, which force is responsible? That is gravitational force. We understood it. The settling properties of particles could be categorized into classes. The settling properties of particles could be categorized into there are four classes. So the names are discrete particle settling, which we understood a bit, flocculent settling, we understood a bit, hindered settling and compression settling. So we will understand these things with few MCQs also with the help of few MCQs. Give some examples of sedimentation tanks. So first we need to understand like in how many ways settling phenomena can be observed, how many units. So we'll see this. Like in grid chamber, we can see for removal of sand and grits. So the water will pass through this grid chamber in around 2 minutes maximum, around 2, 3, 4 minutes maximum. So water will pass in 2, 3 minutes through the grid chamber, so that only sand will settle and organic matter will not settle in the grid chamber. While in plain sedimentation tank, it will take around maybe 3, 4 hours to pass through that. So in grid chamber, we use the gravitational settling in plain sedimentation tank for settleable solids, chemical precipitation tank like we saw in coagulation aided sedimentation for removal of very fine particles, suspended particles by adding coagulants, septic tanks in households you may have seen for doing sedimentation and sludge digestion together in household septic tanks. This is the purpose. Secondary settling tanks after ASP, active sludge process, or after trickling filter treatment. Trickling filter treatment. So these are the applications of sedimentation tank. So this question is MCQ. So we need to match these things with ABCD. So we studied about four types of settling. So now we'll match discrete settling, hindered settling, compression settling, flocculent settling. So particle size increases and terminal velocity increases. So this happens in flocculent settling. So this is for fourth. A hinder particle settle as individual entities. So this happens in discrete settling. Interparticle force due to one hinders the settling of other particle. So the interparticle force of one particle affects the another particle. So that happens in flocculent settling. So that happens in no in hindered settling. Hindered settling. Particles are in such concentration. Means concentration is particles are in such concentration that a whole structure is formed. So this happens in uh, compression settling. And I told previously, like particles are in so much in close contact with each other that when they settle, the water comes out of the interstices. Water comes out of the interstices or voids. Discrete particle settling sedimentation is characterized by particles that settle discretely at a discrete particle will settle at a constant velocity. A particle is there, let's say, at a constant velocity it will settle. Because while deriving the Stokes law, what we consider total force is equal to zero, and force is equal to mass into acceleration. So we are saying like total force acting on the particle is zero. This is gravity force, drag force, and this is buoyant force. Total force acting on the particle is zero, so the Fg is equal to Fd plus Fb. So if we solve it, we say then we get the equation of settling velocity. So that velocity is constant throughout the tank. So that velocity is called terminal settling velocity. So in that case, we uh, took an assumption like force acting on a particle, external total force acting on the particle is zero. The force will be zero means acceleration is zero. So if acceleration is zero means it is moving at a constant velocity, and that constant velocity is terminal settling velocity. Constant settling, constant settling, and this is also hint is also given in derivation. We have taken force is equal to zero. So in that case, mass cannot be zero. Mass cannot be zero. If force is equal to zero, so mass cannot be zero. Acceleration is zero. In dash, the particles remain in a fixed position with respect to each other, and particles settle as a whole. And particles settle as a whole. This happens in hindered settling. Hindered is actually type 3 settling. In settling chamber, the contacting particles tend to settle as a zone, maintaining the same relative position with respect to each other. Then the phenomena is known as. In settling chamber, the contacting particles tend to settle as a zone. They settle as a zone, maintaining the same relative position. So if the distance is like x1, x2, they will settle it like this only. X1, x2. At t is equals to 0, at t is equals to t1. So the distance will be same. This phenomena is called hindered zone settling. Hindered settling. During this type of settling, the liquid tends to move up through the interstitial of the contacting particle. This is compression settling. So due to the compression, the water present in the interstices comes out. This is due to the compression. So this is called compression settling. Which among the following is correct expression of drag force for the particle settling discretely? So this you might have studied in fluid mechanics. So drag force is half CD density of water, a area where projected area into velocity whole square. So in which it is following half CD rho a u square. So the answer is D. Drag force is nothing but uh, if you travel in any medium, let's say air or water, So there is a force due to fluid which exerts force on the surface in opposite direction of the flow. So that force is called drag force. What is the unit of hydraulic surface loading or surface loading? What is the unit of hydraulic surface loading or surface loading? So the units are in terms of how much volume is supplied in a unit area per unit time. How much volume of this is not Q actually. Let me explain it further. How much volume of water supplied in a unit area per unit time. So it is like meter cubed per meter square per day. This will be meter square. It is the answer is A, I think. Yeah. The settling of discrete particles can be calculated using Stokes law. It is Stokes actually, not Stokes. It's with the help of Stokes law. So equation of Stokes law is this: G density of particle, density of particle. This is the fluid. Uh, mu f is dynamic viscosity. The dynamic viscosity of fluid, and dp is diameter of particle. dp is diameter of particle. So the units of dynamic viscosity is Newton second per meter square. dp is in meters only. What are the four zones in sedimentation basin? These are not types of settling. These are four zones in sedimentation basin. Let's study those four zones. So these zones are inlet zone, outlet zone, sludge zone, settling zone. So let's study one by one. So inlet zone is where the water enters. So suddenly water cannot enter and suddenly water cannot enter directly here. Okay. So for that, what we have to do, we have to provide an arrangement of inlet zone so that it can distribute the water throughout the depth. We can see here throughout the depth the water is getting distributed so that constant velocity will be maintained throughout the depth. So this is the work of inlet zone. So in outlet zone, what happens? The water cannot directly go out. It has to go smoothly through weir. Like it will go smoothly in layers through the weirs so that there will be very minimal disturbance. That is the work, that is the use of outlet zone. In sludge zone, what happens? So this, let's understand first settling zone, then we can understand sludge zone. So in settling zone, we calculate the depth of settling zone through some calculations. So we don't want our settling zone, if we provide only settling zone, so our sludge will settle here like this. If our sludge will settle here, so our effective area will be reduced. We designed for this height, we designed for this much height, but we are not getting, it will be reduced. So that's why we are providing this sludge zone, this sludge zone. So settling zone is dedicated for settling purpose, and sludge zone is provided to accommodate the sludge produced during sedimentation process. So these are the four zones in sedimentation basin. Maximum horizontal velocity through the tank, which does not allow resuspension of settled particles, is called maximum horizontal velocity. It is maximum horizontal velocity through the tank which does not allow resuspension of settled particles is called score velocity. SCOUR, score velocity. The score velocity, and this is the expression. So you might have studied this equation in C1 also. C1 also it is used in C1 also. So this K and F depends on the material, and rest things we have studied deeply the die of particle. Determine the settling velocity of spherical particle, which is a particle with a diameter of 100 micrometers with a specific gravity of 2.3 and water at 23 degrees Celsius. Determine the settling velocity of a spherical particle. So the particle we are given the diameter. So let's write whatever is given to us. Diameter is given to us. How much is the diameter? 100 into 10 to the power minus 6 micrometers. So let's write it in meters. 10 to the power minus 4 meters. Correct? And then what else is given? Specific gravity is given G 2.3. What else we need? Temperature is given 23 degrees Celsius. So from book what we'll find out? We'll find out mu and dynamic viscosity at 20 degrees Celsius and mu at 25 degrees Celsius. Then we'll interpolate and we'll calculate the mu for 23 degrees Celsius. So let's find out how much is the mu for at 20 degrees Celsius. Mu is these data I have taken from PV Row environmental engineering book. 10 to the power minus 3 Newton second per meter square at 25 degrees Celsius. 0.890 into 10 to the power minus 3 Newton second per meter square, mu 23 degrees Celsius. So we will interpolate it and we will get it as 0.935 into 10 to the power minus 3 Newton second per meter square. So here what you can see, if temperature is increasing from 20 to 25, its dynamic viscosity is decreasing. So what will happen if you write the formula for settling velocity that we talked earlier also in the first class? If temperature will change, it will affect the settlement of settling or sedimentation of particle. So let me write the equation of terminal settling velocity. So my notations are maybe a bit different than yours, what you are using. Let me write the equation. So G by 80 into density of particle minus density of fluid to diameter of particle whole square divided by b. So if mu is decreasing, if dynamic viscosity is decreasing, if temperature will increase, but we have seen mu is inversely proportional to temperature. If temperature increases, mu decreases. Okay. Uh, so what we can conclude here, terminal settling velocity is inversely proportional to dynamic viscosity and directly proportional to temperature. Check whether it is correct or wrong. So what we can calculate here. So this is the equation. So okay, we'll assume one thing. We'll assume the flow is laminar. Flow is laminar, so that we can use this equation directly. Okay, so I'm writing this. Vt will be 9.81 divided by 182300. G was how much? 2.3. 2300 minus 998.2 into 10 to the power minus 4, that is diameter of the particle divided by 2.935 into 10 to the power minus 3. So terminal settling velocity will come out at 7.59 into 10 to the power minus 3 meter per second. So this is the terminal settling velocity. So what was the question? Determine the settling velocity of the spherical particle with diameter 100 micrometer and specific gravity of 2.3 in water at 23 degrees Celsius. So we have calculated the settling velocity, terminal settling velocity, but we assume that flow is laminar. So we will check whether the flow is laminar or not. If flow is not laminar, we have to iterate it. We have to check, we have to use CD value. We need to change the coefficient of drag, and then we need to use the uh, equations like v is equals to under root 4 by 3. That equation we need to use, and then we need to calculate it. Uh, then we will check for Reynolds number. Check for Reynolds number. So it will be rho Vt d by mu. So the rho here is 998.2 into 7.59 into 10 to the power minus 3. This is the velocity. Diameter of particle is 10 to the power minus 4 divided by mu is 0.935 into 10 to the power minus 3. So it will be 0.810. So which is less than 1. So if Reynolds number is less than 1 or less than equal to 1, then the flow is laminar and our assumption is correct. Assumption is correct. What are the characteristics of an ideal settling basin? So ideal settling basin we'll understand with this question. So ideal settling basin, okay. So it has discrete particle settling, means it will have type 1 settling. 4 zones in the basin that we understood: inlet, outlet, sludge, and settling. and it has even distribution of flow, like uniform horizontal velocity entering the settling zone. Like we will understand it with the help of example. Like in open channel, we have studied like this is the velocity profile somewhat. So we assume like the velocity profile is uniform, even distribution of flow of leaving the settling zone. So what even distribution of flow, uniform horizontal velocity entering the settling zone. So its velocity will be like this. It will be throughout the, it will be BF in the sedimentation time. Even distribution of flow, uniform horizontal velocity, and uniform horizontal velocity I have shown in the previous slide. Like it should be like this, rectangular, not like this. It should not be like this. So even distribution of flow, uniform horizontal velocity entering the settling zone. Even distribute. That's why we are using inlet zone to provide the uniform horizontal velocity. Even distribution of flow leaving the settling zone. Correct. Uniform distribution. That's why we are providing outlet zone here. Uniform distribution of particles. Uniform distribution of particles through the depth of inlet zone. Uniform distribution of particles through the depth of the inlet zone and of the settling zone. So what this is for even distribution of flow entering the settling zone. This is if I point them as 1, 2, 3, 4, 5, 6, 7. So this is for number 3. Uh, I'm not writing. So this is for point number 3. So even distribution of flow leaving the settling zone. So that's why we are providing. That's why we are providing outlet zone. Uniform distribution of particles throughout the depth of inlet zone and of the settling zone. So in fifth, what we are assuming, in point 5, what we are assuming, suppose this is the sedimentation tank, this is the settling zone. So, so here the particles are uniformly distributed at the inlet. The particles are uniformly distributed at the inlet. The uniform distribution of particles through the depth of the inlet zone and of the settling zone. Particles that enter the sludge zone are captured and remain in the sludge zone. So point number 6 says the particles which reached in the sludge zone, the particles which reached here, that we will consider it as removed. This is point number 6. And particles that enter the outlet zone are removed from water. And the particles which are removed at the outlet zone, like we will see the outlet zone here. Particles which reach the outlet zone are considered as removed. These are also considered as removed from the water. So these are the characteristics of an ideal settling basin. What type of settling is observed after addition of alum or iron as coagulant? So the type of settling observed is type 2 settling, that is flocculant settling. Flocculant settling. The volume of circular sedimentation tank is given by the formula. The volume of circular sedimentation tank. So it looks like this. Inlet is from at the center. At the bottom it looks like frustum. So it is a cylinder plus frustum. So the water will come inside and it will leave like this. This is circular clarifier or circular sedimentation tank. So this is frustum, this is cylinder. So the formula is given by this equation. The volume of circular sedimentation tank is given by the formula this. V equals to d square 0.014d plus 0.782 h. So d is the diameter and in meter and h is the water depth. So now we have to solve one question. Calculate the volume of circular sedimentation tank if the diameter is 16 meter and height is 3.5 meter. We just have to put the values here. D is the diameter, so let's write diameter is how much? 16 meter and height is 3.5 meter. Diameter is how much? 16. So it will be 16 square 0.014 into the 16 plus 0.782, height is 3.5 meter. How much will be the value? Sixteen into 0.014 into 16 plus 0.782 into 3.5. I think it is 1153.54 meter cube. Cross check it again. 16 square into 0.014 into the dies 16 plus okay. Whatever, you can cross check it again also. Efficiency of type 1 settling of type 1 sedimentation tank. So first we need to understand how settling takes place. So let's take the example of particles. Suppose we have a range of particle sizes like this. The size is increasing. So let's say we are interested in removing the particle size d naught, and the particle sizes which are bigger than d naught are d plus 1, let's say d plus 2, d plus 3, d plus 4, and similarly the particles which are lesser than this particle size will have dia d minus 1, d minus 2, d minus 3, d minus 4, like that. So we are designing the sedimentation tank for this particle size. Design particle size. So what we assume, so according to the assumption, we are considering these all particles to be distributed uniformly in the in this surface in the initial at the inlet zone and the starting of the inlet zone. These all will be uniformly, all particles are uniformly distributed throughout the depth at the start of the settling zone and at the end of the inlet zone. Okay, here if we see this at the end of the inlet zone, so this is the end of the inlet zone and the start of the settling zone. So here then all the particles will be uniformly distributed. So in this zone only, very limited area, very limited part, all particles will be uniformly distributed. So this is an assumption. In practical reality, it may not be the case, but in this zone, all the particles are present at different height intervals. This is our assumption. Which assumption was this? Uniform distribution of particles throughout the depth of the inlet zone at the inlet zone end of the settling zone. Depth of the inlet zone and, and this will be inlet zone end and starting of the settling zone. And starting of settling zone. Now we'll understand this concept. Efficiency of type 1 settling sedimentation tank. So all particles will be present throughout this uh, throughout the depth at the starting of the settling zone or end of the inlet zone. Okay. Now what will happen? Let's take 2D figure. The particle is designed for, now we are considering only settling zone. So inlet zone, outlet zone and sludge zone are not considered here. So the particle of interest, let's say particle dp, design particle size. So for sedimentation tank, we have to give detention time. So this detention time is designed for this dp particle only. So what we will say, let's say we have designed 4 hours for this particle. So we will say the particle will take 4 hours to reach from this point 1, from point A to point B. So it has a dia of dp. So the particle which has a bigger diameter than this will reach early. Suppose if d is greater than dp, let's say it has a bigger particle size, so it will reach early. So t less than td, it will take less time. So what we are saying, if it reaches at the end of the settling zone, so we will say it is removed. And bigger size particle also, it is removed. Removed. But The particles, if d is less than dp, the particle is smaller than design particle size, so it will not settle. It will not settle. So we consider it as not removed. Not removed. So what we considered, so we have particles size like d now, dp, d plus 1, plus 1, d plus 2. It was, I think, dp or d naught. The design particle or d naught, we took it as d naught also. D minus 1, d minus 2, d minus 3. So their removal will be 100%. 100% removed. We'll consider it in one more way. Suppose the same particle is, we told like the particle is present throughout the depth, uniformly distributed. So if it is present here, this will also be removed. If the same particle is present at lower depth, so it will be removed. Okay. So this is for designed particle. Designed particle. And for big particle, suppose if it is present at less depth, it will also be removed. Is not it? At lesser depth, it will be removed. But for a smaller particle, at a certain height, if it is present at a certain height, then only it can be removed. Let's say the total height of sedimentation tank is capital H, and the height at which the smaller particle removed is small h. Small h. So let's say this particle is d minus 1. Let's say this particle was d minus 1. Let's say this one. So for this particle, the height will be different. And for this particle, the height will be different. So if it is small, the height will be less. So let's say the height is h minus 1. For this, the height is h minus 1. For height, this will be h minus 2 and this will be h minus 3. And the height will be like this only. Understood? So this is not our concern now, just for understanding I am telling this. So now we need to calculate how much is the efficiency of a sedimentation tank in this scenario. So we understood like the design, this d naught will be removed, d plus 1 will be removed, plus 2, plus 3, all those particles will be removed. And the smaller particles, this will be 100% removed. And d minus 1, d minus 2, d minus 3. Minus represents the smaller size particles. So these particles will be partially removed. Partially removed depending on the location or depth, or at what depth they are present. So let's take an example for d minus 1. So percentage removal we are calculating for smaller particle percent. Let me change the color. Smaller size particle. Let's say W is the concentration of total particle, and at particular height, W by H into small h divided by W. Both are W. This will be the efficiency. W will be cancelled. What we are saying, all the particles, all the similar, if d minus 1 particles are present here, they will also be removed. Be- At below this height, all these particles will be removed like this. Okay, and through this edge, what we can conclude like if we divide it by t, we can get velocity. So for this, we can calculate it like Vs minus 1. Vs minus 1 is for velocity of smaller size particle, and Vs is the design is the settling velocity of design particles. Size. So the percentage removal, if it is laminar flow, you can calculate it as Vs minus 1 by Vs into 100. And if it is laminar flow, we can write it as diameter of smaller size particle divided by diameter of either d naught, or we can write it as or dp into 100. Okay, so this is only for laminar flow. So how total efficiency we can calculate? We'll understand clear bit here. We have different sizes of particles ranging from we have different sizes of particles ranging from small to big, like this. So what we'll do the sieve analysis. Yeah, we have different sizes of particles. So we'll do the sieve analysis. And in sieve analysis, we'll plot the weight fraction retained with respect to dia of particle or settling velocity. Okay, let's say the particle size minus d4, it has weight fraction of this much minus it will be like a plot. It will be like 0 to 100. Okay, so it may have little bit this, it might have this much. Let's write the x-axis first. D minus 1, d naught, d plus 1, d plus 2, d plus 3, d plus 4, like that. So let's say we have designed for d naught size particle. So what we'll do the sieve analysis. Whatever retained, we'll plot the graph. So let's say D2 has weight fraction of this much, D minus 1 has this much, it has this much. So we'll plot the graph like this. So what we'll get to know, right? The particle size greater than D naught. will be fully removed. Let's say this is 40%. So this 60% will be removed. 60% removal will be fully removed, and this 40%, some small particles, are partially removed. So this we will calculate using this formula. Let's say this is delta x1, delta x2, delta x3, delta x4. Like that we'll calculate. So the efficiency will be, I'm taking it as 40% here. So 1 minus this, I will take it as 1 minus this, 1 minus 40. 100 minus 40% plus, for small particles, delta x1 part will be removed. How much delta x part will be removed? We are taking it as average velocity here. D0 d minus 1 by 2 divided by uh, the initial. We are using this formula for calculating this. Delta x into Vs minus 1 plus V naught divided by 2 divided by V naught plus delta x2 Vs minus 2 Vs minus 1 divided by 2 divided by V naught. So likewise it will continue. So what we can conclude, so if it is in percentage, you will multiply it with 100. So 100 minus big delta x plus summation of delta xi Vsi plus V naught divided by 2 V naught. So this is the efficiency of a sedimentation tank. This I denotes this value and this xi denotes these mass fractions, different mass fractions. So this is how we calculate the efficiency of a settling basin. Type 1. So this is about today's live session. So